Yes. I think, see, the participants we have, the next session we have a session from Dr. Vivek. I think Vivek is online. Dr. Vivek?
Yes,
yeah.
Yes, ma'am.
Can you share your slide, please? So that just we'll check whether.
Are you able to see this?
It is coming. Yes. You're audible as well. Okay.
Yeah.
Yes. We will introduce you to the participants. After that, we'll start. Okay. Dr. Vivek.
Yeah.
Yes, dear participants, now let's move on to the next session. So for this session, we have another young, dynamic academician and an active researcher, Dr. Vivek Mohan from NIT Trichy. On behalf of Division of Electrical Engineering and the organizing team of this FDP, I am extremely happy to welcome Dr. Vivek for his talk on modern trends in risk and reliability assessment of power systems. Now, for the information of the participants, I'll give a brief introduction of Dr. Vivek. So, Dr. Vivek has graduated from Amrita University in the year 2009, and he had his master's from Government College Trichy with specialization in power system in the year 2011. He received his PhD from Asian Institute of Technology, Bangkok, Thailand for his work on stochastic optimal energy, reserve and risk management in microgrid. He also did his postdoc in the Hong Kong Polytechnic University, Hong Kong. He has served as teaching faculty in different engineering colleges and joined NIT Trichy in the year 2018. He has got a good number of publications in reputed international journals like IEEE Transactions, Elsevier, etc., and has got a large number of international as well as national conference publications. He has also wrote a book on transmission risk optimization in interconnected systems, risk-adjusted available transfer capability, in the book on research advancement in smart technology optimization and renewable energy. In the electrical department of NIT Trichy, he is the principal investigator of the SPARK project on transactive energy markets in Indian power distribution system, sanctioned by from MHRD. So there are a few research scholars working under him in the area of risk management and reliability of power system. He's a reviewer to many IEEE and Elsevier journals, and also he used to deliver expert talks in conferences and FDPs. I'm sure that Dr. Vivek would be able to share a lot of valuable inputs to the participants of this training program. With this brief introduction, let me welcome Dr. Vivek for the session once again. Over to you, Dr. Vivek, please.
Yeah, ma'am. Thank you for your kind words. I'm not wasting time now. I'm just getting into my presentation. Let me first switch off my video and then I'll go to my presentation. 1 minute. I hope you are able to see the presentation. Can somebody respond?
Yes, Dr. Vivek, yes.
Yeah. So the topic today for my presentation deals with modern trends in risk and reliability assessment of energy systems. And below that, you can see one subheading also, perspectives of modeling uncertainty. In general, power system reliability addresses the issues of service interruption and power supply losses, as you may know. Conventional models of power system reliability include outage probability, then failure rates and faults. But if any of the component fails, the whole system may fail according to the topology. Because if it is series topology, then if any of the component fails, then the whole system may fail. And failure of one of the components in parallel connection demands sufficient emergency backup, as you know. In modern power systems, we have considerable penetration of renewable energy, which extends to distribution networks also nowadays, making them active distribution networks. And we know that most of the failures in the power systems occur in distribution networks. Hence, the main challenge of modeling risk and reliability in energy systems is to combine the outage probability of each component in the power system with the uncertainty models of renewable generation. This has become very important. And that's one of the aspects of this particular presentation. So as modeling uncertainty is taken as one of the aspects, the presentation goes a bit analytical, so it may consume some time. But in the initial phase of the presentation, I will move a bit slow, so that you can get into the topic, because most of the aspects are from statistical point of views. Then after that, I may rush through if there is no enough time, then I can rush through. Now, another aspect of risk is with respect to power markets, where profit of the stakeholder and price variations come into play, because we know that now the end consumer is also a stakeholder in the distribution system. He can be paid for curtailing his load or shifting his load, so such aspects will also come into consideration. In that case, we may be forced to model the profit of each stakeholder in the market. It can be utility, it can be an aggregator, it can be a consumer, it can be a prosumer. Prosumer means an entity which produces and consumes energy in the distribution system. So with this, I'm moving into my presentation. These are the contents of my presentation: the risk and reliability perspective, the generic perspective of risk and reliability, then uncertainty modeling. Mostly the 80% of this presentation deals with modeling the uncertainty in power systems. This includes conventional reliability indices and some new indices which came after the emergence of renewable energy in power systems. Then some indices which came from financial portfolio theory and now being adapted to power system and energy accordingly. Some of these indices are Markowitz portfolio theory and conditional value at risk. Then some of the stochastic models which we use for modeling uncertainty are interval arithmetic and affine arithmetic. So these are also discussed in this particular presentation. Now, coming to the term risk, probability of loss or damage to human beings or assets. That is a generic definition for risk. And risk and reliability are two facets of the same fact. Higher the risk means lower the reliability. The need for risk management and quantified risk assessment. What is the need for risk management and quantified risk assessment in power system? That is another aspect. So I'll just give you an example here. Suppose you have, I'm giving you an example here. Suppose you have a PV panel connected to a DC to DC converter, connected to a DC to AC converter, which means an inverter. Now this is connected to a line filter connected to the grid. Suppose this is a rough topology for a PV interface to grid. So what about the risk in this particular system? You need to consider each component and its failure rates, right? Each of these components and its failure rate, so that the whole system is in service or not. We can check whether the whole system is in service or not. So as this is connected in series, any one of the component fails. If any one of the component fails, then the whole system is down, right? So basically we need to find the up and down probability of up and down probability of each component based on the statistical occurrence of failures for each component. Now we divide the states of each component into two. Suppose any of the component is down, then we represent it by 0. Then so D is 0. Then if any of the component is up, we represent it by 1. So these components, DC to DC converter, line filter, DC to AC converter, these components have only two states, either up or down. And if you know the probability of availability in the sense up state, probability of availability is up state, probability of unavailability is probability of down state, then these are two-state probability models, these components. Now, what is the difference between these components with the PV panel? PV panel is a bit different because the PV panel may be in service, but enough power may not be there. That depends on the solar irradiance. So this is not a two-state model. We cannot divide it into just into two states, binary states like 1 and 0. We have to go for multi-state model here. So combining the multi-state model of, in general, renewable energy sources with the two-state models, two-state outage models of the components in power system is what is done in nowadays in the emerging modern power system with sufficient renewable energy penetration. Now you can see the basic steps involved in system risk evaluation here. Determining component outage and generation uncertainty models. What is component outage? I have already mentioned each component. For each component we have two-state model and we can find the component outage probabilities. Then determining component outage and generation uncertainty model. What is generation uncertainty model? That is with respect to PV. In which location it is being installed and what is the resource available there. Based on the statistical history of the resource availability, we can make the stochastic model of PV generation from there. Then selecting the system failure states. What are the system failure states? Basically these up-down states only. Or for the PV panel, it may be some other. It may include some other states also. Maybe in a shaded condition, we may not get enough generation output. So that can be a kind of unavailability from PV side. And calculating their probabilities, evaluating the consequence of selected states. So how this will affect the system or how this will affect the profit of the investor. That means if this panel, I have drawn here a very small scale model, but if it is a PV power plant in which an investor has invested some amount, then the sustained shading condition or sustained unavailability of the system in service may affect the profit of the investor. So this is actually the first definition which we gave for risk. Probability of loss or damage to human beings or assets makes sense here, because this can be a loss for human being or it can be a loss for, technically a loss for the system itself. This is technical and this is financial. So in this case, it is important to model risk and reliability. Now we can see here some applications. What are the applications given here? Component bar topology selection. As you can see from this example, you may have more options to replace one of the components of this particular model. Maybe this DC to DC converter could be replaced by another model, or this topology itself could be changed, right? We have central topology, then string topology, other topologies are there. So micro inverter topology. So we can go for multiple topologies. For each topology, we have to check the system failure rates, whether each component, what is the outage probability of each component and what is the total outage probability of the whole system. So based on that, we can select the topology. So one of the applications is to select the suitable topology. Then now coming to the second point here, long-term planning, capacity expansion, installation planning. That is, before the installation itself, before the installation of the generating source itself, we should plan the size of the source. Then we should locate the source. That means the site of the source should be properly identified so that enough resource is there. So these things are also important for in long-term planning. So if you use multiple sources, suppose I'll give you another example. If you are using both PV and wind in your active distribution network, then the whole active distribution network is working on PV source, wind, then you are installing a battery, and you are taking some power from the grid also. So at any time, the total load demand is okay. The total load demand is satisfied from these sources, right? Now, if we want to size these sources separately, then we have to know the percentage of each source to be installed, right? Based on the install capacity. That is what I am saying. In terms of long-term planning, the sizing is important with respect to installation planning. Installation planning in the sense, the total load demand is fed from how much percentages from each of these sources. That is what is done. Now, operational planning. 1 minute, slide has gone. Okay, now comes operational planning. What is operational planning? Some static tools are mentioned here: load flow, unit commitment, economic dispatch, optimal power flow, ATC estimation, etc. When are we doing these things, these exercises? What is the importance of these exercises? Once we install the sources, once we install the system, after installation, we have to know how to operate this. Right. So for that, we are running load flow. We may run unit commitment. We may run economic dispatch. We may run optimal power flow, and we may run available transfer capability estimation. So for these things also, uncertainty is a factor. Suppose you are working on load flow. I will give you another example. Suppose you are working on load flow. So initially I am going to show with 2 buses only. Suppose mostly we are going for distribution systems. So I'm drawing here a radial system. Now you have a transformer here. So this is the substation level. So this is one feeder in which this is node 1, node 2, and node 3. You have loads here. Now, you know that the voltage at node 3, VN3, VN2, at node 2, VN2, then at node 1, VN1 could be found by executing the load flow or running the load flow, keeping the active and reactive power at the nodes constant, at a constant level. So we are assuming that these are PQ nodes. Wherever loads are there, these are PQ nodes. Suppose you are running a backward forward sweep power flow, backward forward sweep power flow. So fixing this active power and reactive power, is it a good assumption? If you have, if this is an active distribution network, and if you have a micro renewable energy source here, suppose you have a PV panel here, suppose you have a micro wind turbine here, suppose you have a fuel cell here. So fixing the power at any node, whether it is a reasonable assumption, it may not be, because the output from renewable energy is always varying, and we are running this prior to the actual time horizon in which the time horizon in which under consideration. Because suppose we are looking for a time interval 1 p.m. At 1 p.m. we have an idea of load forecast. We have an idea of load forecast. We have an idea of generation forecast. Generation forecast can be from PV and wind, right? So based on this, you are fixing this P and Q. So at any node, the active and reactive power injections depend on the forecast now, and not the actual value. because this is a static tool, right? Load flow is a static tool, and we are doing this prior to the actual horizon. But when it comes to the actual time horizon, what happens is your forecast may not be correct, right? The forecast may be there can be some deviations from the forecast. So this P can be some P plus delta P, or P minus delta P, or this Q can be Q plus delta P, delta Q, or this Q can be Q minus delta Q. Like this happens at each node. And the uncertainty in power injection at every node affects the other nodes also, because that's the way load flow is executed. So what will you do for this? What is the solution for this? This is the importance of modeling risk in static tools. This is applicable for economic dispatch also, because in economic dispatch, what we are going to do is some function which is normally taken as cost. This is cost, suppose cost. Minimizing the cost function is what we do, and f of x, y, z. What is this x, y, and z? Suppose this is active power output from one of the sources P1, active power output from the second source P2, active power output from the third source P3. So our aim is to minimize the operational cost and find the optimal P1 star, P2 star, and P3 star. That is our aim, right? Now, the active powers, these sources may not be dispatchable always. If we are, again, if renewable energy sources are there in the system, we know that they are not dispatchable. So expecting a particular amount of power or the optimal power output from that particular source is not that realistic. So these variables these independent variables of the optimization problem are becoming random variables. They are not deterministic now. Rather, we can only say that P1, if it is a power output from PV panel, then we can only say that P1 has this much probability to take this particular value. P1 has some other probability to take another value. Like that only we can say. That is why these are considered as random variables now. So a deterministic optimization problem is slowly shifting to a stochastic optimization problem. Stochastic optimization problem. Another aspect is now after the deregulated power markets, development of deregulated power markets, even in distribution systems, markets are penetrating, right? There are local energy markets inside distribution system itself. Of course, this is not a scenario of India. I'm explaining this with respect to international experience. In many countries, they are using, they are utilizing the controllable loads, then other avenues to make the distribution system itself a market. So this can be termed as a prosumer market. That means it has a lot of prosumers where they not only consume power but they produce power also. That is a concept. So here price variations are another important factor, because if you are dealing with an hourly market, every hour price is varying. So based on price variations also, your output of the sources and your consumption, our consumption varies, because you are also a stakeholder. So there is self motivation to control from your side, right? So in that case, price also is a factor. So cost cannot be a single factor for economic dispatch from now onwards. That means operational cost means normally it depends on fuel prices only, right? But we have taken price considerations also. According to the grid power price, the power is injected to the grid and power is consumed from the grid, or rather power is sold to the grid and power is purchased from the grid. So price is a function of cost, of course, because we are expecting some percentage profit also. So for any price, you expect that at least the cost should be compensated, right? You are fixing a price for your own local energy produced. So at least the energy cost you want to compensate, right? So this the operational cost plus some percentage profit will be your rupees per kilowatt hour. or the price for 1 unit of energy. So variations of price, then variations of power. So everything comes into consideration while modeling sources and loads in stochastic systems. That is what we are going to, different approaches to model uncertainty in energy systems for risk and reliability assessment is what is going to be discussed in the coming slides. Now coming to the first slide, two popular indices are shown here: loss of load expected and loss of energy expected, or in some books you will see loss of load expectation and loss of energy expectation. What is this? So you assume that you have an installed capacity. The green line shows your installed capacity, but you have an outage, right? So after the outage, the available power is this horizontal line, this one. This horizontal line is the available power. And a load duration curve is drawn here. This is an annual load duration curve. That means this time period is for 1 year. Why it is always in the declining direction? What is this declining pattern? Because we are starting from the highest load value and towards the lowest load value we are drawing this. That is, throughout the year we are checking what is the peak value of load. From there we are starting. Now you are traversing through all load value occurrences of this particular year. That is what you are doing here for drawing the load duration curve. Now after the capacity outage, you can see that this ramp kind of thing, this part during this period, that is in the period Tk, load is more than the generation, because now the available generation is this much only after the capacity outage. Now the total time period is capital T. So what is loss of load expectation? This is represented in terms of hours per year. That means the time period in which generation was not able to feed the demand, or there is generation outage, the time period in which generation outage is there. So Tk is the time period in which generation outage is there here. So Tk by T, if you take Tk by T, then you will get the, what will you get? Then you will get the probability of this one, the loss of load expectation that you will get. Now you can see here the mathematical expression here, sigma j equals 1 to ng, where number of generation source, this is number of generation capacity levels, and sigma I equal to 1 to nl, where nl is the number of load levels, then pi into pj into iij into t. So t is the total time period, right? Now you can see here iij, this value is 1 only when load is greater than generation. So because this is the only outage condition, this is not an outage condition. Here enough generation is there to feed the demand. So this is the outage condition. So in this condition only this becomes 1. So basically iij is the notation which represents outage. Okay. Now pi, what is pi? That is the probability of each generation level, and pj is probability of each load level. What is load level and what is generation level? See, we cannot have a continuous load duration curve like this, because all load values may not have occurred in the same year, right? We may not get all the load values. So what you are going to do is a range of load you are going to select. Suppose 100 kilowatt to 95 to 100 kilowatt. This is selected as one state 1. Now 90 to 94 kilowatt, this is selected as state 2. Now the occurrence of load values in between this range throughout the year gives the state probability of state 1. This is the load state probability of state 1. Similarly, you can find for each range. So you may not be able to get values for each and every load value, 100, 99, 98, all values may not have occurred in the same year. So that is why we are going for ranges here. So these are load levels. Similarly, we are going for generation levels also. If you have a solar panel or a wind power wind turbine in the system, then you are going for output of generation as ranges. So here also you are going like this: 4 kilowatt to 5 kilowatt, or 4 kilowatt to 4.5 kilowatt output, PV output. This can be generation state 1. Like that, generation state 2 would be there, generation state 3 would be there. Like that, you are dividing the generations into states. That is what is this NG and NL. So both generation and load demand are divided into different states, and probability of each state is found out. So we get the state probability. So state probability is multiplied here, right? State probability is multiplied here to the total time period. That is how we get the loss of load expectation. Now, another popular index is loss of energy expectation. What is loss of energy expectation? That is represented in terms of kilowatt hours, right? That is in terms of units, it is found out. So we know that as per the definition of loss of load expected, this is the time interval in which the system has an outage over a time period. That means annual outage happens during this period only. So if we are able to find the energy, the corresponding energy for this time period, then you will be able to evaluate the loss of energy expectation. So that is what we have with these two indices. Now, how these two indices are used, that is the next thing. Because as I told you, we have to take two considerations. One is outage models. What is outage model? Each component has up and down probability. It can go, it can fail, right? Each component can fail. So there is a failure probability according to the number of failures per year, right? Now, the second thing is generation model. Generation model is a multi-state model like what we have seen now. Generation model, that means for PV, wind, etc. we have taken here different ranges, and multi-state model we have considered. For each state we are finding the probability. Similar to this, we have state load models also. For loads also, it is a multi-state model. So this is basically multi-state model. This is two-state model. That means for component outages, we are taking 1 or 0 only, binary values. Okay, so we want to combine these two to get a realistic reliability index or a risk model. Now, coming to outage models. A system consists of two 10 megawatts and one 15 megawatts generating units with the identical unavailability of 0.03. So you have 3 units. 2 of them are 10 megawatts and one of them is 15 megawatts. And each of these units have identical unavailability of 0.03. That means 3% is the unavailability of each of these units. Now, you see the table here. If 0 is the availability, then outage is total capacity is outaged. Now, that means 35 is fully outaged. 10 plus 10 plus 15. This is 35 total outage. So this is outage. Now, what is the probability for this particular state? This 0 state, that means the system to be totally unavailable. So 0.03 is the unavailability of first unit, right? 0.03 is the unavailability of second unit, and for the third unit also 0.03. So we multiply everything because here outage it is simultaneously happening, right? Simultaneous outage of all the units. So we multiply everything, and this is the probability of this particular unavailability. That is, the system is not producing any output. For this is the probability. Now, suppose availability is 10 megawatts. Then this 10 megawatts can be available in 2 ways, because you have two 10 megawatts units. One of the 10 megawatts can be up and the other can be down, or it can be vice versa also. 15 megawatts is of course down. So here you are taking availability of one of the 10 megawatts units, that is 0.97. 3% is the unavailability, so 97% is the availability. So 0.97. Into 0.03 is the unavailability of the other unit. Then 0.03 is the unavailability of the 15 megawatts unit. And this can happen in 2 ways. So into 2. So that will give you the probability of this particular state. Similarly, you are finding each state probabilities. This is with respect to outage probability. because you know that it can have every unit can have only two states here. Either it can be 0.97 that is available, or it can have 0.03 that is unavailable, right? These are the two states. But here it was not like that, where we have seen the load probability ranges, because you are taking here 95 to 100 as a range, right? 90 to 94 as a range. So here for different states, different probabilities are there, right? The panel is in service, right? The PV panel is in service, but enough generation may not be there. That's all. So if that particular generation, suppose the panel produces 96 megawatts, then that comes under this particular state probability, 95 to 100 kilowatts range. Okay, that is what we are doing here. Now, discrete load probability distribution. This is what I mentioned about the state divisions of load duration curves, because you cannot get a continuous duration curve. Rather, what you are doing is you are dividing it into different ranges, and for each state you are finding the probability. Now you see, another aspect is that if you are considering the uncertainty of load also, you are not only considering the uncertainty of generation, you are going to consider the uncertainty of load also. Can you say that for the whole state, this particular state, I'll show you here, for this particular state, for all these values, is the probability same? This is one state, right? State 1. This is state 2. So can we say that state 1 has a particular probability value? Can we say? That may not be realistic. To make it more accurate, what you can do is, for different values of loads here, what we are going to do is the same. This range is L1. Here, instead of megawatts, this is a megawatt range, L1. Okay, this L1 is some range 94 to 98 kilowatts. This is another range, L2. This is some 99 to 103 kilowatts, suppose. Now, can we say that the whole state or the whole range has the same probability? Because 95 may have a different probability according to the frequency of occurrence from the statistical data. Now 96 can have a different probability. So you may have to consider uncertainty at each levels. How will you do it? You can have probability distribution curves at each levels, right? That means it has a mean and it has a standard deviation, right? Standard deviation and mean. So in this range itself, inside the range itself, different values of loads are taken at different probabilities according to the historical data. But what you need is, either you need to make this a single value. You need to make this a single value. How will you make it a single value? What is the single value representation of this particular probability distribution curve? It can be the expected value, right? It can be the expected value. Otherwise, we call it as mean. But since probability is defined here, that is why a more generic definition is expected value. That is why I have taken expected value. So at each range, at each load range here, we can find the expected values. So that gives the representation of that particular load representation or megawatt representation of that particular range. Now, I'm once again going to the first slide here, risk and reliability introduction. Parameter estimation in outage models are represented as point estimation, interval estimation, and distribution estimation. What is distribution estimation? That is what we have shown here now. This one. Each load range is considered as a distribution. So multiple values are there. If you want a single point from here, you are going for expected value. That is what is point estimation. Point estimation. So point estimation, distribution estimation, and the third one can be interval estimation. What is interval estimation? If you know that this particular load value is from 94 to 98 kilowatts, this can be represented as an interval, which is 94,98. This is the minimum value that can be taken, and this is the maximum value that can be taken. So that is what is interval estimate. So this is an interval estimate. This is a point estimate where we take the expected value. It may not be expected value always. Okay, this is one example. I'm just giving you one example. Then it can be a distribution estimation also. Now, coming to uncertainty of loads. So at each load range, we are going to define the probability distribution curve. So you may be fitting this to some known distributions. What are some known distributions? It can be Gaussian or it can be some other distribution. So normally we for loads we fit it into a normal distribution, right? So in between, if some values are missing from your statistical data, what will you do? Because all these values of loads may not occur in a year, right? So what will you do to fit this? One option is you can generate those sorry, you can generate those values using Monte Carlo simulation. That means you are randomly generating some values in between these values so that you can fit into a normal distribution. So this is one aspect of load uncertainty. Similarly, we can go for generation uncertainty also. Now, component outage probability. We already discussed that two models are there. One is two-state model for component outage, and another is multi-state model for generation outage. Not generation outage, generation uncertainty. Now here the two-state model of power conversion system for different topologies is obtained using the series reliability block diagrams. What is series reliability block diagram? If suppose n number of components are connected in series, like what I shown in the example of the PV integration to grid, suppose n number of components are connected in series. Now for each component, there is a up probability and a down probability. So you need to find P down and P up. How will you find it? Suppose lambda is the downtime. Throughout the year, if you take one component is down for this much time period, if you know that, then another component is up for this much time period for throughout an year. Then if you have the idea of uptime and downtime of each component for a particular time period, then you can find the probability up and probability down. Mu by mu plus lambda. That means in the denominator, you are taking the total time, uptime plus downtime. That is the total time. In the numerator, you are taking only the uptime, right? Mu is the uptime. So uptime by uptime plus downtime, that will give you the probability of up, right? Up probability. You are getting the up probability of each component and down probability of each component. So that's how you get the failure rates of each component. So this is a two-state model. Right. This is a multi-state model. Here we find the multi-state model for load. Similarly, we find the multi-state model for generation also. I'm not going to the multi-state model of generation now because it is in the same way we are taking it. Instead of load ranges, you go for generation ranges in renewable energy sources, and you are fitting it to some known distribution curves, and you are finding either the point estimate or the interval estimate or the distribution estimate. That is what you are going to do. Now, this is one example. This one of my master students did this exercise in which we have considered three topologies: central PV system, string PV system, and microinverter PV system. For these three topologies, what we are going to do is, for each component, we are finding the two-state probability, and wherever multi-state probability is, multi-state model is applicable, there we consider the multi-state probability also. Here what we have considered is, for the solar array, we have considered multi-state model, and for the load also, we have considered multi-state model. For all other components, we have considered the up and down probability, and hence we have considered the two-state models. And we have combined the two-state models and multi-state models to find the reliability indices LOLE and LOEE, loss of load expectation and loss of energy expectation. So basically our decision is to select the topology, which topology is best for a particular location. At that particular location, we have an idea about the resource availability, right? So whether it is solar irradiance or wind velocity, we are aware of the resource availability at that particular location, and we are also aware about the failure rates of these components. So based on that, we are going to select which topology is the best. That was the exercise. Okay, for more information, you can go through this particular reference. Now, again, the modeling of load uncertainty is the same thing. I'm just rushing through this. Okay, another aspect is expected load carrying capability. What is expected load carrying capability? It is the extra load that a system can carry after addition of new generating unit without changing the risk level. This is applicable for capacity expansion planning, right? See, the whole reliability aspect is important, or it is emphasized for in the planning horizon only, because we are not aware of the real-time horizon. That is why we plan, right? The real-time horizon, what we plan and what is happening in the real time is something different. So always this uncertainty is there. There comes the importance of modeling uncertainty and defining all these indices and getting the stochastic models, getting the probabilistic models. All these things are important while planning. It can be operational planning or long-term planning, as I mentioned in the first slide. If it is long-term planning, then before installation itself, you are doing it. You are doing the sizing of generation, you are doing the siting of generation, etc. If you are doing it from the operational horizon, you are running the load flow, you are running the economic dispatch, you are running the unit commitment, and you are trying to get a better idea of the real-time horizon, right? A realistic snapshot of the real-time horizon. That is what we expect. Now here, this is this expected load carrying capability. This index is important for capacity expansion. Now you see the plot. We will see how this is important. The blue line shows that the total load is only fed by conventional generation. That is, some fuel-based generation is used for feeding the load. That is the blue line. So the peak load is going to increase. So suppose we are considering a variation of peak load from 165 to 205. You are going to increase the system load from 165 to 205. So what happens when the load is increased with the same generation capacity? What will happen to loss of load expected? What is loss of load expected? It is hours per year. It is represented in hours per year. That is outage hours per year. So if you increase the load keeping the capacity constant, then of course your hours of outage will increase, right? That is why this variation is increasing. This blue variation is increasing, right? For this conventional generation only. Now you are expecting some increase in load in the coming years. So you want to increase the size, or you want to expand the capacity. That is what is your objective. So you are taking two options. You are considering two options. One is expanding the capacity with solar. Another is expanding the capacity with wind. So the orange curve shows that the system is expanded with solar PV capacity. It is expanded with the capacity of solar PV panels. Now it has become the orange curve now. Obviously your generation has increased, right? Earlier this much generation was there. Suppose this is 100% generation here. Now it is 130%, 30% increase has occurred here. When you shift to the orange curve. So your generation is increased and you are analyzing the same LOLE with the same variation 165 to 205. So you have more generation. So what happens to the LOLE now? What about the outage hours? It will be reduced, right? That is why for the same peak value here, you have a lower LOLE for orange curve, right? But at a particular point, both the blue curve and the orange curve has the same LOLE, right, at a particular point. But this point, the same LOLE point for conventional generation is at 185 megawatts for conventional generation. But when you expanded the capacity, the same risk or the same LOLE is happening at 191 or 192. So there is a 7 megawatts difference. That means when you expanded the capacity using solar PV, at the same risk, the system can take an additional load of 6 to 7 megawatts. That is the meaning. So ELCC is the extra load. Once again, you come to the definition. You come back to the definition. ELCC is the extra load that a system can carry after addition of new generating unit without changing the risk level. So without changing the risk level, that means without changing the LOLE value, you have, after the expansion plan, what happens to the load, how much additional load can be taken. Now, what is this gray curve? You are replacing this solar with wind. You are not expanding with solar, instead you are going for wind. So the same expansion, suppose this was 30%, the same 30% expansion is being done with the help of wind resource. Then you can see here that according to this particular location, you are getting a better load carrying capability for wind, because an additional load is taken here. It is near to 194 or 194.5 here. So from 185, it became 192 when you use solar. Instead of solar, if you used wind, then from 185, it became 194. So the extra load that can be carried by the system at the same risk level while expanding the capacity with a particular resource, solar or wind or whatever, that has been found out in this particular analysis. So this is another aspect of risk, because when you go for expansion, you should know that at the same risk level, what should be the additional load you can take. But what is another side of this particular analysis? For expansion, there is some cost, right? There is some cost associated. So if your sole aim is to increase the expected load carrying capability, you have other options. Maybe you can install batteries. In case of renewable energy sources, the outage hours could be reduced by installing batteries, or you can expand your capacity like anything. You can have a bigger capacity, but there is a cost that is incurred here. So what should be your planning decision in this case? You have to trade off between cost and reliability always, right? If you expect more reliability, then of course additional cost is incurred. If you expect to reduce the cost, if that is your sole objective of optimal planning, then what will happen? The reliability is affected. So basically what you should do is you have to keep both the objectives in mind, and you have to trade off it. You have to find a compromised solution and plan the system accordingly. Okay, now this is what is ELCC. Okay, application to Markowitz portfolio theory. I don't have a watch. Can somebody tell me what's the time?
Sir, 11:53.
Okay, so shall I stop now? I'll just go through it and I'll wind up. Okay, that's better. Okay. So another aspect which we use here is Markowitz portfolio theory, which has come from financial investment portfolio theory. Suppose you have a capital investment amount of 1 lakh rupees. You want to invest this amount into different assets. You are putting it in some amount, you are putting it in bank, some amount you are putting it in stocks, some amount you are putting it in mutual funds. If you are doing like that, what will be the portfolio return? Portfolio means this weights in the sense the fraction of investment, the fraction of the capital you have invested in one particular asset. That is the weight of that particular investment, right? So if you change these weights, or if you vary these weights, suppose 10% is put in bank, 30% is put in mutual fund, and 60% is put in stocks. So these weights you can vary always. So accordingly, your returns will also change. The returns in terms of finance will change. Your financial return will also vary. So this aspect, how will you apply in energy portfolio theory? That is one of the modern trends in portfolio planning, energy portfolio planning. What you are doing here is risky assets. You know that stock is a risky asset, right? Its value can change according to the market, and your return may be affected. Bank is a fixed return kind of thing. It has no risk, but the return is less, right? Now, mutual fund has also some risk, but not as high as stock. So some are risky assets, some are non-risky assets. Similar to this, we map this to energy portfolio theory, where renewable energy sources, if you have a total generation capacity, if you want to expand your total generation capacity, which is considered as 100%, suppose it is 100%, this 100% generation capacity can be mixed among several sources. this can be PV, this can be wind, this can be diesel, this can be fuel cell. Okay. This can be fuel cell. Now you know that these are risky sources, PV and wind, because the generation what we expect may not be obtained from these particular sources. But these are dispatchable sources where fuel is used. But we know that as per the operational cost, this has ideally no cost of generation. These sources have no generation cost. So your returns may be, your returns in financial returns may be high from these sources, but your energy returns have more risk among with these sources, or these are non-risky assets, diesel and fuel sources, fuel cell. So the same portfolio theory is applied here, and you are going to find the optimal portfolio. What is the optimal portfolio? Similar to what an investor is doing in financial portfolio, the amount of money that should be invested in bank, mutual fund, or stocks. The same thing you are doing here. The energy, the total energy capacity is mixed among PV, wind, diesel, or fuel cell, based on risky assets and non-risky assets. So this is what is done in Markowitz portfolio theory. But anyway, I'm going to wind up at this point. See, earlier I thought of going a bit descriptive, but later I thought that from application point of view, I don't know the audience, I don't know the kind of audience present here. So I thought from research scholars point of view, it is better to move in an application point of view. How to approach these challenges, that is better. So that is how it was prepared. So sorry for the delayed presentation. Anyway, I'm winding up here. So anyway, I'll just rush through the summary. So combining the two-state component outage model and multi-state model of renewable generation, this was discussed first. Then we discussed about capacity expansion planning, where we introduced the index ELCC, expected load carrying capability. Then application of modern portfolio theory to energy portfolio optimization. At this point, we just stopped our presentation. Then some other aspects are there. Maybe sometime we can discuss these things. If you have any queries, you can just ask.
Thank you, Dr. Vivek. In fact, we should say sorry for you because we could allot only 1 hour for you. So this is also a very vast topic. So you may not be able to introduce and explain in detail about all the topics. So now, so far, I think, yeah, one query is there. Shall I read it out for you?
Yeah. Can I see it from here?
Hello.
Can I see it from here?
Yeah. If you're if you stop sharing, then you can read it.
Okay. So any rule to find the rating of energy storage requirements in a particular...
No, sir. The last question. You see the last question. The previous one.
Is there any effective?
Yeah. That's the question.
Is there any effective way for the EV aggregators to manage the revenue risk, as there is uncertainty in electricity prices that affects the profit? Of course. This is a relevant question with respect to the current research. Renewable. Suppose you are an operator of a microgrid, and you are also the owner of the microgrid, which means you have invested for the sources and infrastructure for the microgrid. But different stakeholders are there in the microgrid. Operator is one stakeholder, but other stakeholders include the EV owners, that means the electric vehicle owners, and the local source owners. That means whoever has the local energy source as rooftop solar PV or micro wind turbine. So profit is not a single thing now. Profit is divided among all stakeholders, right? So as far as an EV aggregator is concerned, EV charging and discharging is occurring at different times at different levels. So there is a spatial and temporal uncertainty in electric vehicle charging and discharging, because time to time your state of charge in the battery is changing, it is varying. So accordingly the power injected at a particular node is varying. That means a particular EV is, we are expecting that particular EV at a particular parking lot, but that is not there at the at that particular time. So that can happen. This uncertainty is always there. That deals with the uncertainty of state of charge. Another uncertainty is spatial uncertainty. The first one I explained is the temporal uncertainty. The second one is the spatial uncertainty, because the EV can be in another parking lot rather than being in the parking lot in which we expected it to be there. So we have to properly stochastically model the spatial and temporal uncertainties of EV aggregators so that we can find the profit of the EV aggregator as a function of these variables. That means the EV aggregators profit is a function of some independent variables, but these independent variables are random variables. They are uncertain in terms of spatial and temporal variations of electric vehicles. So in that case, profit will in effect, consequently the profit will also become a stochastic variable. You cannot say that a particular profit will get, rather we may go for an interval estimate of profit, or a point estimate of profit, or a distribution of profit. That means profit will itself have a probability distribution curve, where we can only say that for getting this much profit, this is the probability. For getting this much profit, this is the probability. That can be one aspect, or we can represent it in terms of interval itself. That means profit minimum, comma, profit maximum. That can be another aspect. Now it is also mentioned about uncertainty in electricity prices. Of course, that also will affect this dependent variable. This is dependent variable, right? Profit is your dependent variable. Your independent variables are power injections at each, the charging power, the discharging power, those things in at each node. So since those independent variables are uncertain, profit is also uncertain, and profit is also a function of price, right? Price into power, that is what will give you the profit. Your expense, your revenue minus your expense. Revenue is a function of price and power. Expense is a function of price and power, and consequently profit is a function of price and power. But both price and power are uncertain, so profit is also uncertain. So you may need to find a probabilistic model here. One of the aspects, one of the approaches can be a probabilistic model. That is how we find it. I think we can, if one of some references I can provide, I can just post the link here. You can go through it for this particular topic. Anything else?
Yes, Dr. Vivek, I think we will stop here for the time being. So once again, sorry for you for not allotting the sufficient time. And definitely we should plan another session from you in some other programs, some other training programs. Hope you will be happy to associate with us.
Thank you very much. Actually, I have posted a link here. This paper gives an idea of profit maximization of EV aggregator, considering the risk in state of charge as well as availability in the parking lot. The paper which I have posted here.
Okay. Thank you very much. Thank you, Dr. Vivek. Participants, we can leave the session now and rejoin at 1:50. Afternoon also we have 2 sessions. Thank you, Dr. Vivek.